Section: Introduction. In this section, we introduce the advancements in user-facing AI systems, particularly those powered by large language models, LLMs, like ChatGPT. These systems have become adept at handling complex tasks, including answering questions, solving math problems, and generating code. Recently, there has been a growing focus on AI agents, systems that can perceive their surroundings and take action. These agents are evolving to perform intricate tasks such as software development, navigating websites, managing household chores, and even conducting scientific research. As AI agents tackle more complex challenges, we face new difficulties in their development and evaluation. To address this, there have been numerous initiatives to create open-source frameworks that support the development of these agents. Typically, these frameworks consist of three main components. 1. Interfaces for agents to interact with the world, like function calls or code execution. 2. Environments where agents operate. And 3. Communication methods for interactions between humans and agents or between agents themselves. These frameworks simplify the development process in various ways. When we design AI agents, we should also consider how humans interact with the world. Currently, the most effective way humans engage with their environment is through software, which influences every aspect of our lives, from basic logistics to advancements in science and technology. Given the significance of software and the tools available for its efficient development and deployment, it serves as an ideal interface for AI agents to engage with the world in complex manners. However, creating agents that can effectively develop software presents its own set of challenges. We need to explore how to enable agents to create and modify code within complex software systems, provide them with tools to gather information for debugging or task-related needs, and ensure that their development is safe and does not negatively impact user systems. In this paper, we present OpenDevin, a community-driven platform aimed at developing both generalist and specialist AI agents that interact with the world through software. OpenDevin is not merely a theoretical framework. It also includes a fully functional implementation of agents, environments, and evaluation methods. As of now, OpenDevin features an agent hub with over 10 implemented agents, including a robust generalist agent based on the Code Act architecture, enhanced for web browsing and code editing. User interaction occurs through a chat-based interface that visualizes the agent's actions and allows for real-time feedback. Additionally, our evaluation framework supports 15 benchmarks to assess our agents. OpenDevin is released under a permissive MIT license, which allows for commercial use, making it suitable for a wide range of research and practical applications in both academia and industry. The platform has gained considerable popularity, with 28,000 stars on GitHub and over 1,300 contributions from more than 160 contributors. We see OpenDevin as a catalyst for future research innovations and diverse applications driven by a broad community of practitioners. We will describe how to use OpenDevin to 1. Define and implement an agent. 2. Understand how each action execution leads to an observation. 3. Manage and extend commonly used skills for agents. And 4. Compose multiple agents to solve tasks. An agent in OpenDevin can perceive the environment state, which includes prior actions and observations, and produce an action to execute a user-defined task. The state is a data structure that contains all relevant information for the agent's operation, including an event stream that records past actions and observations, such as the agent's actions and user interactions. This state also includes additional information necessary for the agent's functioning, like the cumulative cost of LLM calls and metadata for tracking multi-agent tasks. Inspired by Code Act, OpenDevin connects agents to their environments through a core set of general actions. These actions allow the agent to execute Python code and Bash commands in a secure environment. There is also an action for interacting with a web browser using a specialized language for browsing. The action space is designed to be flexible and powerful, enabling agents to perform various tasks using different tools, such as Python functions or REST APIs. Users can easily define tools using programming languages supported in OpenDevin and make them available to the agent through a straightforward function calling interface. Furthermore, the framework allows agents to create their own tools when necessary. Observations are the changes in the environment that the agent notices, which may or may not result from the agent's actions. These can include natural language messages from users, the results of the agent's previous actions, or other relevant information. The agent abstraction in OpenDevin is designed to be both simple and powerful, enabling users to create and customize agents for various tasks easily. The core of this abstraction is the step function, which takes the current state as input and generates an appropriate action based on the agent's logic. By providing this abstraction, OpenDevin allows users to focus on defining the desired behavior and logic of the agent without getting bogged down by the technical details of action execution. Section Summary. In this section, we introduce OpenDevin, a community-driven platform designed to facilitate the development of AI agents that interact with the world through software, featuring a comprehensive implementation of agents, environments, and evaluation benchmarks. We highlight the platform's capabilities, including a user-friendly interface for real-time interaction and a flexible action space that allows agents to execute code and perform tasks effectively, while also addressing the challenges of building software developing agents. Section: Agent Runtime. How execution of actions results in observations. In this section, we describe the agent runtime, which provides a versatile environment for our agents, allowing them to perform a variety of software development and web-based tasks similar to what human developers do. This includes handling complex software workflows, analyzing data, and browsing the web. Our agents can access a Bash terminal to execute commands, use a Jupyter notebook for writing and running code in real time, and interact with a web browser for various online tasks, such as seeking information. For each task, we create a secure and isolated environment using a Docker container, where all commands from the agent are executed. We connect to this environment through a secure protocol, allowing the agent to run commands and receive the results as observations. We also set up a workspace directory within this secure environment, where users can place files for the agent to work on. Additionally, the Linux environment supports an interactive Jupyter server, which our agents can use for executing and debugging Python code. We implement a web browser based on Chromium, which interacts with our agents through a set of defined actions like navigating, clicking, typing, and scrolling. After performing these actions, the browser provides detailed observations about its current state, including the structure of the web page and visual elements. We can enhance these observations with additional attributes to help agents better understand the web pages they interact with. Next, we discuss the agent skills, which emphasize the importance of a well-designed agent-computer interface, ACI, for effectively solving complex tasks. We recognize that creating and managing a wide range of tools can be challenging, especially when we want to make them accessible to various agent implementations. To address this, we developed the Agent Skills Library, which serves as a toolbox to improve our agents' capabilities by providing utilities that go beyond basic command line functions. The Agent Skills Library is structured as a Python package containing various utility functions that can be easily imported into the Jupyter environment. This design makes it simple for community members to contribute new tools, as defining a Python function as a tool is straightforward. The flexibility of Python packages allows different agent implementations to utilize these tools through a core action we defined. We ensure that the tools in the Agent Skills Library are rigorously tested and maintained, following best practices in software engineering. Our inclusion criteria focus on adding new skills only when they are not easily achievable by the agents themselves or when they require calling an external model. Currently, our library includes utilities for file editing, such as modifying existing files and scrolling through them. We also provide tools for reading multimodal documents, like extracting information from images and reading text from PDFs. A complete list of the skills we support can be found in the relevant section of our paper. Finally, we enable cooperative interaction between multiple agents through a special action type called Agent Delegate Action. This allows one agent to delegate specific subtasks to another agent. For instance, a generalist agent with limited web browsing capabilities can delegate those tasks to a specialized browsing agent, enabling more complex web interactions. Section Summary. In this section, we describe how Agent Runtime equips OpenDevin agents with a versatile environment for executing a variety of software development and web-based tasks, utilizing tools like a Bash terminal, Jupyter Notebook, and a Chromium browser within a secure sandbox. We also introduce the Agent Skills Library, which enhances agent capabilities with specialized tools, and explain how agents can collaborate through delegation to efficiently tackle complex tasks. Section: Agent Hub, a hub of community-contributed agents. In this section, we discuss Agent Hub, which serves as a platform for community-contributed agents. Based on our agent framework, OpenDevin offers a variety of agent implementations that users can select from, providing a foundation for different tasks. We introduce the Code Act agent, which is our default generalist agent built on the Code Act framework. At each step, this agent can either engage in conversation with humans using natural language to seek clarification or confirmation, or it can execute tasks by running code. This includes executing commands in Bash, Python, or other programming languages specific to browsers. This broad range of actions allows the agent, starting from version 1.5, to handle various tasks such as editing files, browsing the web, and running programs. Next, we present the Browsing Agent, a generalist web agent designed to be a straightforward yet effective baseline for web-related tasks. This agent is similar to the one used in Web Arena but features enhanced observations and actions, relying solely on zero-shot prompting. At each step, the agent provides the language model with a description of the task, the actions it can take while browsing, its current observations from the browser, previous actions, and an example of action prediction that includes reasoning. The expected output from the language model includes this reasoning along with the predicted next actions, which may include finishing the task and reporting the results back to the user. We can extend this agent to create more advanced web agents or allow other agents to use it through delegation. We also introduce the GPT Swarm agent, which innovatively uses optimizable graphs to build agent systems, integrating different language agent frameworks through a modular approach. Each node in this system represents a specific operation, while the connections between nodes define how they collaborate and communicate. This structure allows for automatic optimization, which helps in developing multi-agent systems. Additionally, OpenDevin supports the creation of microagents, which are specialized agents focused on specific tasks. These microagents leverage most of the implementations from existing generalist agents, like the Code Act agent. This design aims to make agent development more accessible, enabling community members to share specialized prompts that work well for their unique needs. Users can create a microagent without any programming by simply providing its name, description, input and output schema, and optionally a specialized prompt that guides the generalist agent toward specific tasks. Examples include the Commit Writer agent for generating Git commit messages and the Typo Fixer agent for correcting typos throughout a code repository. To systematically monitor our progress in developing generalist digital agents, we have integrated 15 established benchmarks into OpenDevin. These benchmarks cover areas such as software engineering, web browsing, and various forms of assistance. In this section, we compare OpenDevin to open-source baselines that do not involve manual prompt engineering tailored to the benchmark content. For brevity, we will refer to OpenDevin as OD throughout this section. In our results overview, we aim to create general digital agents that can interact with the world through software interfaces, as illustrated by the code actions we described earlier. We believe that a software agent should not only excel in code editing but also in web browsing and other supportive tasks, such as answering questions about code repositories or conducting online research. Our evaluation results, which we present in a table, show that while OpenDevin agents may not always achieve the highest performance in every category, they are designed with versatility in mind. Notably, The Code Act agent, without any changes to its system prompt, shows competitive performance across three main task categories: software development, web interaction, and various other tasks. This is particularly noteworthy when compared to baseline agents, which are usually optimized for specific tasks. Focusing on software engineering, we report results from specific benchmarks. The SWE bench is designed to evaluate agents' abilities to solve real-world issues on GitHub, such as bug reports or feature requests. The agent interacts with the repository to address the provided issue through file editing and code execution. The modified code repository is then tested against a suite of tests that include new tests added by human developers for the same issue. Each test instance comes with hint text, which offers natural language suggestions for solving the problem. Throughout this paper, we present all results without using hint text. We have also created a simplified version called SWE Benchlight to facilitate efficient testing, and we typically use this subset for cost-saving reasons. In our results, we find that the latest version of the Code Act agent, version 1.8, using the CLAUDE 3.5 Sonnet model, achieves a competitive resolution rate of 26% compared to other open-source agents that specialize in software development. We also evaluated the same agent using the GPT-4o mini model, which solved only 6.3% of the problems but did so at less than 1% of the cost compared to other models. Section Summary. In this section, we present OpenDevin, a platform that supports various community-contributed agents, including the Generalist Code Act agent, which can perform tasks through natural language interaction and code execution. We also introduce specialized micro-agents for specific tasks, evaluate our agents against established benchmarks, and highlight that our Code Act agent demonstrates competitive performance across software development, web interaction, and other tasks, despite not being optimized for any single category. Section: Human Eval Fix. In this section, we discuss our findings from various benchmarks that evaluate the capabilities of our model, OpenDevin. First, we look at Human Eval Fix, where we task agents with fixing bugs in a given function using provided test cases. The bugs are designed to ensure that at least one test case fails. We concentrate on the Python subset of this benchmark and allow our models to debug themselves over multiple attempts, using feedback from test execution. Following the setup from previous work, we measure success using a pass rate at different thresholds. Our results show that OpenDevin Code Act agent successfully fixes about 79% of bugs in the Python subset. This performance is significantly better than all other non-agent approaches, nearly doubling the performance of StarCoder 2 to 15b. While SWE agent achieves an even higher success rate of 87.7%, it benefits from a full demonstration of a successful bug-fixing trajectory, whereas our evaluation of OpenDevin is done without any prior examples. Since Human Eval Fix was created by humans and all bugs were carefully validated, we believe that achieving a perfect score of 100% on this benchmark is entirely possible, and we aim to reach this in future versions of OpenDevin. Next, we examine MLBench, which assesses agents' abilities to tackle machine learning tasks across 18 GitHub repositories. This benchmark includes over 9,000 tasks covering 169 different ML problems, requiring agents to generate Bash scripts or Python code based on user instructions. In a controlled environment, agents can execute commands iteratively and receive feedback, helping them understand the context of the repository and progressively meet user needs. Following the original paper's setup, we evaluate agents on a quarter of the MLBench tasks. Our results indicate that OpenDevin agents using GPT-4o achieve the highest success rate of approximately 76.47%, surpassing SWE agent, which has a success rate of about 42.64%. We observe that performance declines with less capable models, highlighting the effectiveness of OpenDevin in handling complex ML tasks. Additionally, we notice that our agents show promise in reducing errors and misunderstandings compared to non-agent approaches in the MLLM bench settings. We then turn to Gorilla API Bench, which evaluates agents' abilities to utilize APIs. This benchmark includes tasks related to TorchHub, TensorHub, and Hugging Face. During evaluation, models are presented with questions about API usage, such as identifying an API that can convert spoken language in a recording to text. We assess correctness based on whether the model's API call is appropriate for the task. Our results reveal that OpenDevin, using GPT-4o, achieves a success rate of 36.4%, outperforming baseline models that were not specifically fine-tuned for API usage. Although Gorilla shows better performance on API Bench, it is important to note that it was fine-tuned specifically for API tasks. Next, we discuss Tool QA, which evaluates agents' abilities to use external tools. This benchmark includes tasks on various topics, such as checking flight status, coffee prices, and data from Yelp and Airbnb. It requires the use of different tools, including text, database, math, graph, code, and system tools. Tool QA features two difficulty levels, easy and hard. Easy questions focus on single tool usage, while hard questions require more reasoning. For our evaluation, we use the easy subset to assess tool usage capabilities. Our findings show that OpenDevin with GPT-4o achieves the highest performance compared to all baselines. We note that agents excel in tasks involving CSV and database tools but need improvement in using math and calculator tools. We also evaluate Biocoder, a benchmark for code generation at the repository level, specifically targeting bioinformatics tasks. This benchmark assesses agents' ability to retrieve and effectively use context. While the original prompts included relevant context, we removed this information in our study to demonstrate OpenDevin's capability for context retrieval, self-debugging, and reasoning through multiple interactions. Biocoder consists of 157 Python and 50 Java functions, each focused on specific areas in bioinformatics, such as proteomics and genomics. The benchmark aims to generate code in existing repositories where the relevant code has been masked. Our results indicate that OpenDevin, using GPT-4o, achieves a success rate of 44%, outperforming all non-agent baselines that rely on prompting, where GPT-4 alone only managed 6.4%. Biocoder proves to be particularly challenging for non-agent methods, as they lack repository-level retrieval capabilities, which are essential for accessing important information like global variables and function declarations. Finally, we discuss BERT, a benchmark for text-to-SQL tasks, which translates natural language into executable SQL queries in realistic and large-scale database environments. We selected 300 samples from the development set to integrate into OpenDevin and evaluate execution accuracy. Additionally, we enhanced the setting by allowing the agent to engage in multi-turn interactions to refine the final SQL query, enabling it to correct previous results based on the outcomes of SQL execution. Our results show that OpenDevin with GPT-4o achieves an execution accuracy of 47.3% on a subset of BERT, demonstrating its potential as a SQL agent. This performance surpasses that of prompting-based approaches using code language models, such as CODELLAMA7B Instruct, which achieved 18.3%, and CODEQWEN7B Chat, which reached 31.3%. Section Summary. In this section, we evaluate the performance of OpenDevin across various benchmarks, demonstrating its effectiveness in fixing bugs, solving machine learning tasks, utilizing APIs, and generating code for bioinformatics and SQL queries. Our results show that OpenDevin consistently outperforms non-agentic approaches, achieving high success rates in complex tasks while highlighting areas for further improvement. Section: Web Browsing. In this section, we present the evaluation results for web browsing benchmarks. First, we discuss Web Arena, which is a benchmark that we can host ourselves. It allows web agents to choose their own paths to complete tasks. Web Arena includes 812 tasks that have been carefully curated by humans, covering various areas like shopping, forums, developer platforms, and content management systems. Each task comes with a test case that checks if the agent has succeeded, for example, by verifying the status of a web page element or the text returned by the agent. From our results, we observe that our browsing agent performs competitively compared to other agents that utilize large language models, LLMs, with general prompting techniques. Some agents, like AutoWeb GLM, need manual adjustments specific to the web arena tasks. This highlights the trade-off between using a generalist agent versus a specialist one tailored to a specific domain. We have chosen to use a more general browsing agent as a foundational component in OpenDevin. Next, we look at Mini-WAB++, which is an interactive web benchmark featuring built-in reward functions. It consists of tasks initialized on 125 minimalist web interfaces. Unlike Web Arena, the tasks in Mini-WAB++ are simpler, requiring fewer steps and providing detailed step-by-step instructions. Some tasks do require visual capabilities, and many existing works focus only on a subset of these tasks. However, we report performance on the entire set and only include baselines that have been evaluated on the full set. Our results show that our generalist browsing agent completes nearly half of the tasks without needing to adapt to the environment. However, because Mini-WAB++ is synthetic, agents that have been specifically trained for these environments using reinforcement learning or human behavior cloning have nearly reached peak performance. This indicates an even greater trade-off between generalist and specialist agents compared to the more general Web Arena benchmark. We also report results for miscellaneous assistance benchmarks. One of these is Gaia, which assesses agents' general task-solving abilities across various real-world scenarios. It requires a range of capabilities, including reasoning, multimodal understanding, web browsing, and coding. Gaia consists of 466 curated tasks across 3 levels. Traditionally, setting up Gaia has been complex due to the need to integrate various tools with the agent, but OpenDevin's infrastructure simplifies this process significantly. In our experiments, we achieved a score of 32.1 on the first level of Gaia, which is a notable improvement over the original AutoGPT. Gaia's performance is sensitive to the support of multimodal input and web navigation skills, suggesting that we can achieve even better scores as OpenDevin's infrastructure continues to improve. We also evaluate agents using GPQA, which tests their ability to use tools effectively when solving challenging graduate-level problems. This benchmark includes 448 difficult multiple-choice questions in subjects like biology, physics, and chemistry. Using tools, such as Python for calculations and web searches for relevant information, helps agents answer these questions more accurately than LLMs alone. Our results indicate that OpenDevin's integration of diverse tool use and web search capabilities allows our agent to solve complex multi-step problems more effectively, surpassing the previous state-of-the-art by 9.6% and 12.3% on the main and diamond subsets of GPQA, respectively. Next, we examine AgentBench, which assesses agents' reasoning and decision-making skills in a multi-turn, open-ended generation context. We focused on the code-grounded operating system subset, which includes 144 tasks. Our agents from OpenDevin interact directly with the task-specific operating system using bash commands in a multi-turn manner, combining interaction and reasoning to complete tasks. In our experiments, we found that OpenDevin's CodeAct agent version 1.5 achieved a score of 57.6% on AgentBench using the GPT-4 model, outperforming the baseline score of 42.4% from the original paper that used GPT-4. Interestingly, when we used weaker models like GPT 3.5 Turbo, our agents generally performed worse than the original baseline agents. This suggests that generalist agents, such as those in OpenDevin, need a certain level of capability from the foundational model, especially in following instructions, to operate effectively. Lastly, we discuss Mint, a benchmark designed to evaluate agents' abilities to solve challenging tasks through multi-turn interactions using tools and natural language feedback simulated by GPT-4. We used the coding and math subsets from URIS for our evaluation, following the same setup as the original paper, which allows the agent to interact up to 5 times with 2 chances to propose solutions. Our results show that OpenDevin agents perform comparably to the default agent in the original benchmark, with notable improvements in the math subset. Section Summary. In this section, we evaluate our web browsing agents using various benchmarks, including Web Arena and MiniWab++, highlighting the trade-offs between generalist and specialist agents. Our results demonstrate that while our generalist browsing agent performs competitively across tasks, specialized agents excel in environments tailored to their training, and we also show significant improvements in other benchmarks like Gaia and GPQA through enhanced tool integration and multimodal capabilities. Section: Proofwriter. In this section, we introduce Proofwriter, a synthetic dataset designed to evaluate the deductive reasoning skills of large language models, LLMs. Similar to Logic LM, we concentrate on the most difficult subset, which includes 600 instances that require reasoning through 5 steps. To reduce the chances of errors in understanding the semantics, we utilize the logical forms provided by Logic LM. In our results, we observe that the OpenDevin agent uses a symbolic solver to tackle the tasks, achieving performance that is on par with the leading neurosymbolic model, which is represented by the references we mentioned. Next, we discuss the Entity Deduction Arena, EDA, which assesses an agent's ability to infer unknown entities through strategic questioning, much like the game of 20 questions. This benchmark evaluates the agent's skills in tracking state, planning strategically, and reasoning inductively during multi-turn conversations. We analyze 2 datasets, things and celebrities, each containing 100 instances, and we report the average success rate across these datasets. Our results indicate that the Code Act agent performs comparably to the outcomes reported in the original paper.